So thank you very much for the organizers for the invitation. And I am asked to talk about new physics and mainly related to the flavor anomalies. So far we know that the standard model is too good for us, and basically we pretend that we understand almost everything within it, and we are desperately looking for some signatures of BSM particles. And so far we didn't see any direct signature, and we know there are some reasons why we need to go beyond the standard model physics. So basically the indirect evidence of dark matter and matter antimatter asymmetry. So this has somehow, one can say somehow it has to deal with some kind of cosmological implementation of the standard model of particle physics. And then we have already have some kind of experimental evidences, like we have seen the tiny neutrino masses which were predicted to be massless, and also we have seen kind of very high mass hierarchy between all the fermion masses, what we have actually observed. So these two things, either we can actually extend the standard model and incorporate the neutrino masses, and also for the fermion mass hierarchy, we can see like it's some kind of ad hoc fine tuning is embedded in the standard model parameters. And then we already heard a nice talk by Jian yesterday and also today. So we know the problem of electroweak mass hierarchy. So basically the Higgs mass is unstable under quantum correction, and we somehow think that the new dynamics should show up at the level of TeV range. Basically from these four reasons, indirect or say even direct, we do not see any definite energy scale where we should actually expect the BSM physics, except for this one, the last one. And so far, so the well-motivated popular BSM constructions like supersymmetry, those are some sort of becoming less and less appealing due to the null results from experiments. So in that sense, we can think that we should look for new directions. So whenever I say new directions, it has nothing to do with the new paradigm what we actually learned from the talk by Jian. So here what I mostly talk about, say suppose we concentrate on fermion mass hierarchy and somehow try to relate whatever the hints we have from the low energy data from the so-called flavor anomalies. So just for the younger audience, so what I mean by the fermion mass hierarchy, so basically when we look at the mass scale of the electron and the top, so there is kind of 7 orders of magnitude difference. And when we look at from the Lagrangian point of view, so we see the gauge couplings are same for all the fermions. So there is a flavor degeneracy, and we have a much larger group, which is called the flavor symmetry. And this is again broken by the Higgs-Yukawa interaction. And what we end up getting is like this uses, for example, this is the up-type Yukawa matrix, and then we look at the elements here. So the top quark entry is roughly 1, and all other elements are somehow very small. So this is known to be the old flavor puzzle, like why these masses and the mixings of these standard model fermions, whether there is some kind of reasoning behind this, or all these are like just some accidental thing which is appearing here. So the aim is just somehow to connect this old flavor puzzle with the new flavor puzzles, or say the B anomalies, and we have also heard about these things yesterday and also today. So we have this anomaly which is seen in the flavor changing neutral current B2SLL. The ratio of the muon and electron channel is very well predicted within the accuracy of 1% in the standard model. And starting from like say 2014, LHCb has performed several measurements, and they are consistently seeing some depletion in the prediction compared to the standard model prediction. And these deviations are at the level of 2 sigma. So there is also another channel which is B sub s to phi mu mu. So if we look at the quark level transition, this is again the B2SLL channel. But in this case, this observable is not cleaner one like the ratios, but this is kind of the differential branching fraction. And you can see even for the muon channel in the same Q square range, which is like 1 to 6 GeV square, we see a kind of depression in the data compared to the prediction. And this is at the level of 3 sigma. Then I move to the another one, which is called RDRD Star. We have also heard yesterday in Soumitra's talk. So again, some kind of deviation when we construct the ratios. So these are semi-electronic channels. So whenever we are constructing the ratios, the hadronic uncertainties cancel a lot. And recently LHCb has published their result, which is close to the Bubber measurement. And this red blob is the current world average, which is deviating from the standard model, which is this black error bar at the level of 3 sigma. So in this case, you can see the experimental value is higher than the standard model prediction. And similar thing is also observed, say, another ratio, which is the same quark level transition, B to C tau nu, but in terms of like different mesons in the final state. And in this case, although the uncertainty is quite large from LHCb, but the trend is same, like the data is larger than the standard model prediction at the level. It's less than 2 sigma. And another interesting puzzle, what we have this muon magnetic moment. So what we see, like the main source of uncertainty is coming into this G-2 measurement is from this hadronic vacuum polarization. And Fermilab has confirmed the BNL data. And if we just compare the data with the hadronic vacuum polarization estimates from the data-driven approach, then we see kind of 4 sigma deviation. But of course, there are predictions from lattice collaborations, and also they do not agree among themselves. So, I mean, in principle, we can wait for them to come in an agreement. And even if we say like there is something wrong going on in the data-driven approach, then we also try to somehow alter the electroweak precision data in some sense. So for this talk, I am not going to scrutinize whether these are actually real, the so-called real anomalies, whether there is some kind of experimental flaw or from the theoretical, there is some part is missing. So my talk is mostly based on like, if we are really seeing some hints, then what can we actually infer for the new physics? So then how do we proceed? All these are like low energy processes. So for example, the best tool we have is the EFT. So if we just say like at dimension 6 level, so if we consider the 4 fermion operators, which are constructed from the standard model fields and the symmetry, which are known as the SMEFT, so then we get like 59 operators. Now, if we actually break them into their flavor parts, so then we end up getting like 2,500 operators. So the point is, if we try to identify the non-zero effects in this whole space, so it's kind of hopeless situation to find anything non-zero with this full set. So the idea is like what we always try to use the symmetry assumption. Either we select a subset based on some symmetry on the UV theory, or we somehow treat the anomalies or say whatever the hints we are seeing independently. So why I say treat them independently? Because if we just look at the energy scale which can involve in this EFT operators. So for example, as I mentioned, RK star, those are loop level process in the standard model. So if we just consider this 4 fermion operator and we make no assumption on the Wilson coefficient, so the roughly to explain the deviation, we need the new physics scale to be around 30 TeV. However, for the RDRD Star, which is a 3-level process, so in this case, to explain the anomaly, the scale can be as low as 3 TeV. Now it comes like whether this assumption on the Wilson coefficient is kind of robust. Of course not. you can have different structures depending upon the flavor structure of the new physics. So for example, if we assume minimal flavor violation, that means the flavor violation is only arising from the standard model fields, and new physics operators, they are not involved in this. They do not generate any new source of flavor violation. Then you can see roughly to explain B2SLL anomaly, you can even go to the 6 TeV range because the Wilson coefficient will vary as like the standard model scale, standard model flavor violation. One can also generate the MFV in the new physics context via another loop. So you get another extra loop factor and you can further lower the scale. So in principle, whatever the new physics scale we are expecting from these hints, they actually depend a lot on how we are dealing with the flavor dynamics. Some similar kind of argument can also be made for say G-2 if we just consider the SMEFT leading operator, which is shown here. So without any assumption on this, you can even push the new physics scale to say 100 TeV. And of course, you can lower the scale if you have some kind of new physics model with say chiral enhancement. So that I'm not going into the details. So then since we need to probe the flavor structure of the new physics or say BSM particles, so one of the main ways is to go with the simplified models. That means at least one new physics particle is present at a time, or say, yeah. So you can say some various possibilities, say for B2S, the prime extra dimensional leptoquarks, and in this case, 2 HDMs, W prime and leptoquarks. So leptoquarks appear both the places. And these are nothing but some, say, scalar or vector particle which can turn a lepton into a quark. And it was like tabulated long back. It's not a new idea. It's there from 70s, and it's just revived by, one can say, because of this peculiar nature of the B anomalies. So then again, the question is, suppose we consider this leptoquark scenario. So then how do we determine this Yukawa structure? So the leptoquark coupling with the lepton and the quarks. So one way is just to roughly fit the data. So we have kind of then large number of free parameters in the theory. Another again is we physicists love to use the symmetries. So you assume some kind of underlying symmetry in the UV model, which will not only reduce the parameter, also will give some kind of theoretical motivation to deal with such cases. So as I already mentioned, the minimal flavor violation, which is actually not, you cannot explain the current nature of B anomalies only with this context. So our aim was to extend with the leptoquark scenarios. So what we did, whatever the Yukawa matrices we have for the leptoquark couplings, we made them as flavor spurions. So that means they are kind of auxiliary fields, and they have kind of all the standard model fermions, they have Fogart-Nelson charges, which are like some U1 distinguishable U1 charges for all these standard model fermions. So just to give an idea of how this will work, so let's take a SMEFT operators, 4 fermion operators with standard model quark doublet and lepton doublet. So in a generic EFT, all these C Wilson coefficients are order 1 numbers. So we have kind of 81 parameters. Then if we impose minimal flavor violation only in the quark sector, we're not introducing anything in the lepton sector. So reduce the number of parameters to 6 from here, like 3 complex numbers. So how this Fogart-Nelson charges actually work? So basically, in that case, this Wilson coefficient will go as in the power of some small U1 breaking term lambda, and all these are the generation dependent charges. But in this case, we again end up getting this large number of parameters. So what we did, if we just embed leptoquarks into this Fogart-Nelson scenario, then we can actually divide it into 2 parts, and all these S, they are called these leptoquark spurions, and we have kind of a reasonable number of parameters in context of this 4 fermion operator. So then the standard model flavor structure, we already know the CKM we need to produce, because you remember we have introduced charges for all standard model fermions. So that gives some constants, and also we can then fix the charges for the left-handed quarks up to say a common offset D. And then the left and right combination are also fixed by the Yukawa, the standard model quark and the lepton masses. But the charge lepton mixing is, of course, unknown. So we have a kind of freedom to choose the lepton charges. And what we did, we just took up, huh? Yes. In this case, you can see like, so when we embed the leptoquarks into this spurion business, so then we can actually generate the standard model fermion masses, the flavor structure, and we can, I mean, all these couplings are actually fixed by the charges and the masses. I mean, by the CKM and the masses. So these are not at all free parameters like normal Yukawa couplings for the leptoquarks. So all these are like some fixed quantities which we need because we already have seen these quarks and leptons. So maybe I'll just give you an example. So here you see like these are Yukawa couplings, these S tildes. So in a normal leptoquark case, these are 3×3 matrices. But in this case, what I can show you, okay, in the next. So as I mentioned, so in this case, since the left-handed charges for the quarks are fixed and also some sort in the leptons, and we take into account the constants from all other possible channels, we end up getting only for the two solutions for all these spurions, leptoquark spurions. So these are not at all any free parameter which one can fit the data to get the anomalies or say remain in the constraints. So yes, so then what I was mentioning, so basically we want to explain these channels and then we have constants from all other possible channels because we cannot just turn off one coupling and say this is 0 because we don't need it. Because in this case, it's all related to the standard model flavor structure. And that's why we end up getting only two solutions for the charges are possible for say all these three leptoquark spurions. And with this, so basically we can actually explain the anomalies. So you see in the whole model where there are three new Yukawa couplings, which are 3×3 matrices. So in principle, 27 parameters, we have only 3 parameters in our whole setup because of the flavor structure we embedded there. And so the question is, okay, the discrepancies are reduced, we can explain the anomalies, but what are the other signatures we are seeing? So here are some decay modes where the standard model branching fractions are given in some cases which are 0 and even very small. And the third column is the experimental upper limit. So in some cases, you can see we have kind of huge enhancement compared to the standard model one, and it's just one order less, one order below than the current experimental sensitivity. So it's very kind of easy to say confirm and falsify these kind of scenarios. And this is also kind of normal situation when we try to explain this neutral current and both charge current anomalies, because these are kind of some channels of B decays which relate muon and tau. So just a side remark. So this leptoquark can also contribute to the muon G-2, which I was showing you earlier. So it's a kind of a loop which is dominated by a top quark. And in this case, we end up getting like we are having kind of strong suppression because of this tau to mu gamma rate. And in principle, whatever the solution we have, that only the two choices we have, it's not possible to explain the deviation from the Fermilab data and the data-driven approach, whatever we are seeing now. So in principle, if we had the freedom to choose all the leptoquark couplings independently, it is possible to do, but in this scenario, it is not. So this was just one example to deal with, say, this charge current and neutral current anomalies. So I will just quickly say another interesting channel, which is also a flavor changing neutral current. But in this case, instead of the leptons, charged leptons, we have, say, neutrinos in the final state. So experimentally, it is much more challenging because of the two missing neutrinos, and no signal has been observed in this mode. However, very recently, and we also heard yesterday in Diego's talk, that Bell has come up with a very innovative tagging technique. So in this case, they are using some inclusive tagging technique. So basically, they are not reconstructing the full the B tag site. So they are using some kind of decay topologies to actually balance both the sides of tagging and the signal side. And in this case, they are expecting some kind of signal. Even in this case, they have the result of very preliminary data. So if we just roughly take this into account, and I hope Bill will very soon will have some kind of update on this channel. So at the moment, it goes kind of like 2 times than the standard model prediction with a very large error. So just in another work, we actually tried to see whether this kind of enhancement is possible in terms of some, say, simplified model, which can explain these other charge current and neutral current anomalies, which I was talking in the first part of my talk. So here you see, so basically this S1 and R2, these are different like scalar leptoquarks and vector leptoquarks. This is also Z prime. So in some cases, you can see it's possible to obtain a 2 times enhancement for this B2K new bar channel, or say B2K star new bar channel, if we are really seeing any hint in this anomalous, in this ever changing neutral current decays. And similarly, for the combined explanation, we find like S3 and the U3 is kind of some it can show some desired enhancement in these 2 channels. So of course, measurement for this mode will be very crucial to falsify this BSM setup. So this was just from this hints which we are seeing in the semi-leptonic channel. And just I would like to mention another some kind of puzzle which is also seen in a non-leptonic mode. So this is decay mode where B decays to a D sub S or with a pion. So you don't see any leptons in the final state. And these are kind of, there are 2 more channels in this set. So these are color allowed 3 channels. And you see like different quark flavors in the final state. So there is no possibility of having annihilation diagram or even penguin diagrams. So in that sense, these are, although always these hadronic modes are difficult to deal with, but in that sense, these modes are somehow easier, I would say, compared to the other ones where we deal with annihilation and penguin diagrams. So what is interesting is like currently the theory predictions, which actually uses the QCD factorization, it sees like kind of a huge deviation, like a big, huge deviation what Bell recently has published, I mean, put in the archive. So then the idea is there are 2 ways. Whenever you see deviation, either go and try to build some model, new physics model. So there is this group of people there. In that sense, WPI models are kind of favorite to explain this puzzle, I would say. But of course, you can see these are 4 quark operators. So there are some huge constants on the direct searches, say, if you're going to 2 jets and from the LHC. But in another sense, since these are like hadronic decay modes, so basically the theory estimates has to be carefully looked at, and there has been quite some effort going on to compute the missing pieces from the theory side. For example, the missing part of the form factors, and also some kind of risk scattering effects, which are also evaluated. But in my understanding, we still need more efforts to actually understand the QCD factorization in this mode. So I just try to conclude. So I was trying to show you various puzzles or anomalies in B decays, which are persisting there for, say, several years. So this RDRD Star and also muon G-2 in the other sense. And also this is interesting. I didn't talk about VCB puzzle. I think we heard about it yesterday. So the point is, if we try to really see what kind of new physics effects are there, it might be possible that they are correlated or they are not correlated. I try to highlight in terms of the scales which can be involved in these channels. And also it's possible that there can be some parts from the theory side which is missing, or can be some experimental flaws which can actually lead to evaporation of some of the anomalies. But the point is, like, the flavor physics is not just to deal with these anomalies. These anomalies will come and go, and if we are lucky, we will actually observe or get the hint just like we got for the CERN work. But if we are not, we are in a very crucial time, because LHCb and the Bell, they are running, and they will be running for, say, I don't know, 10 more years. So, and they are actually evaluating so many decay modes where we don't even have the predictions from the theory side. So whatever the number they are given, in some cases we don't know even what to compare. So forget about getting any anomaly in those channels. So my point of view, so a lot to understand from the hadronic side. So theory efforts must be put into this topics. So thank you very much for your attention.
Thank you. Questions? Okay, Dipankar.
Okay, Rusa. So my first question is about this B to S transition that you described. So you discussed leptoquarks, right? I think it is related to the previous question that Tuhin asked. So we know that if we, to the standard model, if we add the leptoquarks, then we can explain those anomalies. But I think your point was if we add it forcefully, then the Yukawa couplings that we introduce, those are arbitrary and you have to fit them retrospectively from the data. And let's say you get them small. So your objective is to basically explain those smallness by embedding the leptoquark model in a Frogat-Nielsen framework, so that smallness of the Yukawa coupling gets translated into number of fermion lines that you introduce, right? But I did not see any like quantitative remark on the, let's say, the flavor symmetry breaking scale or this masses. So does this fit give you any idea about those?
Yes, so those masses the fermion masses you can push up to, I don't know, even Planck scale.
No, I know that is in principle I can push, but if I want to fit the B2S data,
yes,
does that give me any hint about that scale?
Yes, indeed. So it depends on like how you are actually embedding, right?
So you had a model, right?
My model is kind
You
of
you want
low energy. Still it's in the EFT one. I still didn't show you how to actually get those operators with so many fermions in the model, right? So in that sense, it's still not a full model. It's just a framework which is saying how to actually motivate the the EFT operators, the 4 fermion operators from a UV point of view. But for a full model, you of course need the fermions, and then you need to compute the scales.
the SU3 of Q and SU3 of U, and the corresponding Frogat-Nielsen charges, the U1 that you have chosen.
Yes.
Doesn't it look like it's not commuting back and forth? I mean, it's
so
not,
this
isn't it?
one I have chosen, it is not obeying the MFP. It is beyond MFP.
So you have to make sense now. So it's a framework, so it needs to make sense. So how does it make sense to have both SU3s as well as your U1, that particular U1 at the same time?
Maybe, yeah, okay, where is my slide? Okay, I mean, maybe I didn't get your question properly. So you are saying we can't have the U1 on top of the SU3?
No, we motivate that there is a specific, like the MFB, the way you got that polynomial, why you square, y_d square, and things like that.
Yes, so in my case, MAB is not followed. It's the leptoquark is generating extra source of lavor violation. So that was my point, that MAB cannot explain the B anomaly. So we need to go beyond it.
Take like the 8 operators which MFB permits you, and then on top of it you put different Poget-Nielsen constraint.
No, we added extra source of lavor violation through the leptoquarks, through forgotten. So this is not at all MFB framework.
But then you have a large number of operators, no?
So that's what I showed. Like if we have, I can't show the slides, but if you have the Forgot-Nielsen embedded in leptoquarks, so then the number of parameters are for one operator, say 20.
Okay, so then I missed it.
Okay, thanks.
Other questions, comments? Okay.
Just a small comment. You showed the HVP thing as measured from the data and the BMW. Okay, so of course, if one assumes the BMW, then the discrepancy in G-2 goes away.
Not goes away.
I mean, it reduces significantly. But on the other hand, if we accept that, the delta alpha, the fine structure constant, that fitting goes for SX, right? Crevelin et al. Have shown that, and some others too, I think, Marciano. And similarly, some other variables also
goes bad.
So probably it's
We
still
can,
under
we can have
discussion.
somewhere in between. So,
yeah, maybe.
yeah, yeah, thanks.
Okay, if there are no other questions, let us thank the speaker again.